Lecture 2 is reactions of alcohols. This is the second part of our alcohol series. Last time we did synthesis of alcohols and structural properties of alcohols. There was some review in that. Today we're going to see a lot of new reactions, but this is going to be the last true reactions lecture for a while. Remember that we're going to change gears and do spectroscopy for a few days, and then we're going to have the midterm before resuming our normal tour of functional groups. So today's lecture is going to focus on oxidations. Last time we talked a bit about reductions, where we use lithium aluminum hydride or sodium borohydride to reduce various functional groups, ketones, aldehydes, carboxylic acids, and esters into primary or secondary alcohols. Today we're going to look at reactions predominantly that go in the other direction that increase the number of bonds to oxygen. This is a reaction map that I made to summarize all of the oxidation and reduction pathways that are available to us. You can see there's lots of pathways. Some of them are parallel, some of them crisscross, some of them go halfway, others go 2 steps at once. Keep these straight. I'm going to give you a blank reaction map where I've taken all of the reagents out that you can try to fill in to quiz yourself or to help make flashcards, for example. These are important. Using these reactions properly will help us give specific reactions that change certain functional groups on our molecules, but not other functional groups on our molecules. It also helps in synthesis to know what pathways are available for us to go from one starting material or any number of starting materials to one specific product. So let's look at some oxidations of alcohols. The first one I'm going to start with is a very common reaction. It's called a chromate oxidation, where we use sodium chromate mixed with sulfuric acid. This is sometimes called chromic acid as a mixture. This will transform a secondary alcohol into a ketone. Notice what we're doing when we go from a secondary alcohol to a ketone. As the book has highlighted, we're removing the H from the carbon bearing the alcohol and removing the H on the alcohol, and we're replacing those two atoms missing bond with a double bond between the two. That's an oxidation. We're decreasing the number of hydrogens bonded to carbon and increasing the number of bonds of oxygen to that carbon. Here's an example, cyclohexanol. It's a secondary alcohol. We add chromic acid, sodium chromate, and sulfuric acid, and we get cyclohexanone, the oxidation product, at 90% yield. Now that's pretty good for an organic reaction. Sodium chromate is a great oxidizing agent. It is basically a form of chromium 6. If you figure out the oxidation state of chromium in Na2Cr2O7, it's chromium 6. And in the process of oxidizing the alcohol to a ketone, chromium 6 is reduced to chromium 4. Remember that any oxidation also has to have a concomitant reduction along with it. Now, the good thing with sodium chromate is that it's a powerful, fast reaction. The reaction typically goes to high yields, meaning it goes to completion. There are minimal other byproducts around. There's also a color change that goes along with this. Chromium 6, if I recall, is bluish green, and chromium 4 is orange. So you see a color change occur when the reaction is done. That's kind of nice because it gives you a visual cue. But the bad thing is that chromium 6 is really toxic. And remember, chromium 6 is the form that's in the reagent, not the product. So generally speaking, this is a reaction that you don't want to do at high quantities. If you want to oxidize, say, 100 kilograms of an alcohol to a ketone, you don't want to have hundreds of kilograms of chromium 6. It's really toxic at very low levels. On paper, of course, that doesn't matter. If you're using this reaction on an exam or on a homework assignment, it's a perfectly acceptable reagent to use. That's why the book shows it to you. I just want to let you know that kind of in the real world, this is a less than ideal reagent to choose for a relatively simple transformation such as this oxidation. Sodium chromate, however, is such a good oxidizing agent that if you have a primary alcohol, you can do 2 steps, 2 cycles of oxidation. The first oxidation step is parallel to what we just saw with a secondary alcohol, where we're going to remove a hydrogen from the carbon and a hydrogen from the oxygen, replace those bonds with a double bond. That gives us an aldehyde. But aldehyde is also susceptible to a second round of oxidation. That hydrogen that is still bonded to that carbon can get replaced by an oxygen, make it an OH and therefore a carboxylic acid. And now we've gone from having 1 bond to oxygen to 2 bond to oxygen to 3 bond to oxygen. So 2 oxidation cycles. This O in brackets is just shorthand for some oxidation process. Now, sodium chromate will do both of those oxidations in 1 step. Well, it's really 2 subsequent steps, but the point is that you can't stop at the aldehyde. If you start with a primary alcohol and you use sodium chromate, you will get the corresponding carboxylic acid at very high yields, 92%. So that's great if you want a carboxylic acid. You can start from the primary alcohol. It goes through the aldehyde as an intermediate, but you cannot stop the oxidation at the aldehyde. If you want to stop the oxidation at the aldehyde, thankfully for us, there is a way to do that. Again, if you want to start at a primary alcohol and do 1 oxidation cycle, but not the second, the reagent that you want is called pyridinium chlorochromate. It's chromate, CrO3, mixed with pyridine and hydrochloric acid, and the solvent is dichloromethane. This brew creates a reagent called pyridinium chlorochromate, which we call PCC. And PCC is a special reaction because it really is one of the only reactions that will transform a primary alcohol into the aldehyde by doing 1 oxidation cycle, but not oxidizing the aldehyde. It's kind of like the Goldilocks situation. It's strong enough of an oxidizing agent to transform the primary alcohol into the aldehyde, but it's not a strong enough oxidizing agent to oxidize the aldehyde to the carboxylic acid. Here's an example here. 1-heptanol, a 7-carbon chain with an alcohol on the 1 carbon. That's a primary alcohol with PCC and dichloromethane. You get heptanal, the corresponding aldehyde, where the double bond O is on the last carbon. 78%, pretty good yield. Another problem with pyridinium chlorochromate again is that you can see that it's chromium 6. If oxygen is the -2, that's -6 charge, that we've got 1 chromium to balance. So this is chromium 6. It's also pretty toxic. So again, on paper, it's fine. But in the real world, there would be a better choice of a reagent. I'm going to show you that towards the end of this lecture, an alternate reagent that's often used in the real world in place of PCC. So we've looked at primary alcohols to aldehydes. We saw primary alcohols to carboxylic acids, and we've seen secondary alcohols to ketones. Those steps are on our reaction map. Here's a primary alcohol to an aldehyde, primary alcohol all the way to the carboxylic acid, or secondary alcohol to the ketone. These steps that we're covering on individual slides are eventually going to be summarized on our reaction map. So we've done primary and secondary. What about tertiary alcohols? Here's a tertiary alcohol. Notice that the carbon bearing the O that usually loses a hydrogen in this process in a tertiary alcohol does not have that hydrogen. So this is not able to be oxidized. A tertiary alcohol cannot be oxidized to a carbonyl. Imagine if we took this carbon and made a double bond to that oxygen, that carbon would have 5 bonds. It would have 2, 3, 4, 5. So no oxidations on a tertiary alcohol. Again, just a quick summary slide that we just went over. This again, oxidation is the reverse process of reductions. We used LiAlH4 or sodium borohydride to transform aldehydes and ketones back into alcohols. I wanted to show you another way to reduce alcohols even further. Here's a secondary alcohol that if you react this with lithium aluminum hydride or sodium borohydride, there's nothing that the hydride would be able to attack. Basically, it would just deprotonate this H and leave us with an O minus. So if we want to go even further and reduce the alcohol all the way down to an alkane, here's a step we could do. We could first do a dehydration, an elimination using H2SO4 and heat that will eliminate the H and the adjacent OH as water, give us a double bond, that's an alkene, and then we can use a hydrogenation, H2 and platinum, to reduce the alkene to an alkane. This is effectively replacing an OH with an H, but we're doing it by 2 more elementary steps rather than something that won't really work if we were to try it. There are lots of ways to do oxidations of things. There's all kinds of oxidizing agents. Many things that you are familiar with in household chemicals are oxidizing agents. One thing that's available, sodium hypochlorite, NaOCl. This is bleach. Bleach is an oxidizing agent. You can take cyclohexanol, which is a secondary alcohol. It's got an H on the carbon and an H on the O. React it with bleach, you'll get cyclohexanone at pretty good yields, 85%. By the way, oxidation by bleach is one thing that bleaches clothing. If you have, say, a scarf where the fabric has been dyed, say some deep royal purple or blue, the dye is a long conjugated system, and that conjugated system allows the molecules to absorb light of a certain frequency and then re-emit it later. So the dye, being an organic molecule, is susceptible to oxidation. And if you oxidize the dye with bleach, what it does is it disrupts that long conjugated chain and changes the ability of that molecule to absorb certain wavelengths. So instead of your nice blue scarf absorbing those wavelengths, when you react it with a bleach, it will chew up those long conjugated chains in the dye and stop it from absorbing those wavelengths. Another oxidizing agent that we've seen before is KMNO4. We used KMNO4 to make diketones from triple bonds. We used it to cleave double bonds and triple bonds to give us carboxylic acids. We used it to create diols in neutral cold conditions from alkenes. We can also use it to convert alcohols into ketones, the same way that we use bleach or the same way that we use chromic acid to convert a secondary alcohol into a ketone. It turns out that KMNO4, you can also use it in place of chromic acid to convert a primary alcohol all the way into a carboxylic acid. Basically, KMNO4 does the same thing as Na2Cr2O7. These are analogous reagents. There's another reaction called the Swern oxidation, SWERN, Swern, that uses DMSO and oxalochloride at fairly low temperatures, negative 60 degrees Celsius, to convert alcohols into ketones as well. The Swern oxidation is the one alternative to PCC in that it will convert primary alcohols into aldehydes, and it will not convert the aldehydes into carboxylic acids. So in the real world, the ideal or the preferred method of converting primary alcohols into aldehydes is not PCC, but the Swern oxidation. It's a nice mild reaction. None of these reagents are particularly toxic or reactive. You can do it at very low temperatures, so the reaction does not get out of control. It's very gentle to your other functional groups that might be present on your molecule. It also gives off a byproduct that makes it easily detectable when the reaction is done. You can walk in the lab and smell the product, and you know that your Swern oxidation is done. I'll show you at the end of the lecture what the mechanism looks like, because it's kind of cool, but you don't really need to know it for this class. I want to show you kind of a fun example from biology involving oxidation. Your body has an enzyme called alcohol dehydrogenase, or ADH. What the role of alcohol dehydrogenase is, basically it exists to convert ethanol into acetaldehyde. You can see that we are oxidizing a primary alcohol, ethanol, a 2-carbon alcohol, into an aldehyde. The reason that it does this is because ethanol is toxic and acetaldehyde is not as toxic. If you consume ethanol, it will convert that poison into something less poisonous. Acetaldehyde, notice it's an aldehyde, meaning it can go through a second oxidation cycle. It can take the acetaldehyde, do another oxidation cycle, and you get acetic acid, which is even less toxic than acetaldehyde. Acetic acid is a component in vinegar. So this is a safety latch. If you drink ethanol, NAD plus will convert ethanol into something much less toxic. But NAD plus is not a specific oxidizing agent for ethanol. It will oxidize other alcohols. It doesn't care what the alcohol is. If the alcohol can be oxidized, NAD plus will oxidize it. So if you drink, say, methanol, which is a single carbon alcohol, and you do an oxidation cycle, you will get formaldehyde, which is worse than methanol. Methanol is pretty bad for you, but formaldehyde is even worse. And formaldehyde, being an aldehyde, can undergo another oxidation cycle to get you formic acid, which is even worse than formaldehyde. Formic acid and formaldehyde cause blindness. So if you drink methanol, here comes your alcohol dehydrogenase saying, hey, I'm going to save my person from alcohol poisoning, and it oxidizes methanol to formaldehyde and then formaldehyde to formic acid. It's actually hurting you. So don't drink methanol. This is a rule not to drink methanol. Methanol is often found in poorly distilled spirits. When you make alcohol, there is a mixture of many kinds of alcohol, amongst which are ethanol and methanol. And in the distillation process, you remove pretty much everything but the ethanol. So in a poorly distilled spirit, for example, something that's homemade or something that's, say, done in the backwoods of West Virginia illegally in these prohibitionist stills, you tend to get beverages that are high in methanol content, and drinking them can cause blindness because your alcohol dehydrogenase converts the methanol into formic acid. Ethylene glycol has a similar effect. Ethylene glycol is what is an antifreeze. If you oxidize ethylene glycol to primary alcohols, you get this dialdehyde, ethanal dialdehyde, and you go through another cycle, you get oxalic acid, this dicarboxylic acid, also very, very toxic. So it's not really the methanol or the ethylene glycol that'll kill you or make you blind. It's the formic acid or the oxalic acid that they are converted into in your body by alcohol dehydrogenase, which is there in the first place to try to protect you from ethanol. Now, alcohols can be used as nucleophiles. We've seen this a lot. We've seen them used as weak nucleophiles in SN1 reactions where we have a carbocation present already, a strong electrophile. That gives us our protonated alcohol on our carbon. We remove that extra H and we have our ether, ROC. Or we can turn weak nucleophiles into strong nucleophiles using sodium, like sodium hydride. That converts our alcohol into an alkoxide, and we can use a strong nucleophile in an SN2 reaction where we have a weaker electrophile, where we have only a partial positive charge on our carbon instead of a full positive charge on our carbon. So SN1 has a weak nucleophile where we need a strong electrophile. SN2, we have a strong nucleophile, so we only need a weak nucleophile. In either case, you get ROR ethers as your product. We've used these a lot as nucleophiles. In fact, alcohols were the first nucleophiles that we ever used. But they can also be used as electrophiles. This is a class of molecules called tosylate. In this process, we take an alcohol and we react it with something like paratoluene sulfonic acid. This is paratoluene sulfonic acid here. This is sometimes abbreviated as TSOH. This S double bond O with the benzene ring and the methyl is called a tosyl group. So tosyl alcohol or tosyl OH. In this process, the alcohol reacts with the toluene sulfonic acid. The H from the alcohol and the OH from the toluene sulfonic acid come off to make water, and you end up connecting your alcohol oxygen to your paratoluene sulfonic acid sulfur, and this is called a tosylate. I'm going to show you in a minute on the next slide what we can do with tosylates. We're going to use them as electrophiles. I'm going to show you how and why. So this is called a condensation reaction because these two things come together and you get water as a byproduct. Try drawing a mechanism for this. It's kind of a fun mechanism to try to figure out. Remember that carboxylic acids, which is paratoluene sulfonic acid, is like a carboxylic acid. It's actually a sulfonic acid because it's got a sulfur group. These acids are more acidic than alcohols. Keep that in mind. So you're going to protonate your alcohol from your acid, then figure out how these two things are going to come together to make your product. If you can't figure it out, it's in your book, or I can show it to you in class if you need help with that. So rather than making tosylates from paratoluene sulfonic acid here with the OH group, a lot of times what we'll use is paratoluene sulfonyl chloride, where instead of that OH group, we have a chloride here. This is a better electrophile. You need a good electrophile to react with a weak nucleophile like an alcohol. So the reaction is just that the O attacks the sulfur and displaces the chlorine. We then have some weak base like pyridine around to remove that extra hydrogen from our alcohol, and we get our tosylate ester. It's an ROS double bond O double bond O. This is like an ester group, except it's a sulfonyl ester instead of a carbon ester. That OS double bond O is a very good leaving group. That oxygen, if you kick off that whole big group, including this oxygen, will have a negative charge on it. And that negative charge is resonance stabilized. That negative charge can go onto that O or that O. So it's triply resonance stabilized. Since it's so stable, that makes it a really, really good leaving group. This OS double bond O benzene ring methyl group is called a tosylate ion, and it's very stable. It's often abbreviated OTS. So this is ROTS, R-tosylate. And this whole thing, again, is a good leaving group now. So if you have a tosylate like this, and you have a nucleophile like iodide, for example. Now, we've talked about iodide not being a great nucleophile. That's okay, because tosylate is such a good leaving group that a weak nucleophile like iodide can displace it. It's an SN2 pathway for the most part. You'll get inversion. We see that because if we start with S2-butyl tosylate here, we can displace it with an iodide, and we get R2-butyl iodide. We get inversion of the stereocenter. And like you see, displacement of this OTS group, the tosylate. Your book has this table here that shows all of the nucleophiles that can displace a tosylate as a leaving group. So here we have all of our tosylates, ROTS, all the way down. We can displace the tosylate with hydroxide. That would remake our alcohol. That's kind of cool. We can take our alcohol, convert it into a tosylate, then displace the tosylate with hydroxide, get back to our alcohol. We could displace a tosylate with a cyano group, a cyanide, and that gets us a nitrile functional group, where the C- attacks the R and displaces the OTS. We can displace tosylate with bromide. Halides, like we saw, like iodide, attack the R, kick off the OTS. That'll get us an alkyl halide. We could start with an alkoxide, a good nucleophile. We've used these a lot. That would give us an ether. We've made ethers a lot. ammonia we could use. If we displace the tosylate with ammonia, we get an amine salt, RNH3 plus, OTS minus. Of course, we can use base to get rid of this extra H and make just an amine. We can also displace a tosylate with a hydride, like from LiAlH4 or NaBH4. That H minus again would attack the O, displace the OTS, and we get to an alkane. Now, remember that in all of these cases, the tosylate would be made from the alcohol. You just take an alcohol, ROH, reacted with tosyl chloride, TSCl, you get the tosylate. And then in a second step, you introduce the tosylate to a nucleophile of your choice, and you convert it into a new functional group. So think of this as a reaction map. The tosylate is kind of a tunnel, kind of a bridge from an alcohol to an alcohol, or to a nitrile, or to an alkyl halide, or to an ether, or to an amine, or to an alkane. These are very useful transformations. Now, notice that a nucleophile as weak as a bromide could displace a tosylate. That shows you how good of a leaving group tosylate is, how stable that triply resonance stabilized oxygen is. This is an example again of using tosylates as a leaving group for a reduction. Here's a cyclohexanol where you reacted with tosyl chloride that changes our OH into an OTS, that tosylate. The lithium aluminum hydride will produce a hydride that'll attack the carbon, displace the OTS, and we get our cyclohexane. This is a similar step, similar process, an alcohol to an alkane that I showed you up here, where we converted an alcohol into alkane. I went through dehydration, then hydrogenation. They went through the tosylate and then reduction. Now, if you want to replace an alcohol with a halogen, I've just showed you a way to do it. You can convert the OH into a good leaving group by making it into a tosylate and then use bromide to displace the tosylate, and you get the RX. You can do with acid, where you would take your acid, protonate your alcohol, that would turn your OH into water, which is a good leaving group, displace it with an X minus by SN1 or SN2, and you get your RX. But there are some limitations to something like this. You get poor yields, first of all. Secondly, anytime you do an SN1 or an SN2, you have a nucleophile that is susceptible to also acting as a base and getting you elimination products. You can also get rearrangements. If you go through an SN1 pathway, or hopefully not an E1 pathway, you might get rearrangements by moving your carbocation around by hydride shifts or methyl shifts or ring shifts or resonance or something like that. So there's a lot of reasons to try to avoid these types of pathways where you turn a poor leaving group into a good leaving group like a tosylate and then do a displacement. A more direct way to do it, doing it in one step instead of first going through your tosylate intermediate or your water leaving group intermediate, is to react it with PX3. For example, PBr3, phosphorus tribromide. This will take your alcohol, convert the alcohol into a bromine. In one step, you get high yields, 90%. It's a great reaction rather than going through these kind of messy multi-step processes. Here's the mechanism. It's kind of a fun mechanism. It also explains how we get inversion of stereochemistry here. We'll start with our alcohol. Here's, say, a 5 carbon alcohol, 1, 2, 3, 4, 5. That's 2 pentanol, our alcohols on our 2 carbon of 5 carbon chain. The alcohol O is going to attack the phosphorus and displace one of the bromines from PBr3. That gets us this intermediate, this PBr2OH. The O has a positive charge now because it's got 3 bonds. This piece over here, the OH and the PBr2, that big piece is a good leaving group. That O is positive, which means it wants to take a lone pair back. What happens is the bromide will come on and attack from the back side, do an SN2, and displace the HOPBr2. That means we take an R alcohol, react it with PBr3, and we will get the S bromoalkane. This will always undergo inversion of stereochemistry. It's an SN2 reaction. Of course, we could go the other direction, starting with an alkyl halide, use hydroxide, do an SN2, displace the bromine, and get the alcohol. So now we can go back and forth. Hydroxide to make the alcohol, or PBr3 to make the alkyl halide. An analogous reaction will convert an alcohol into a chloride, but instead of using PBr3, you use what's called thionyl chloride, SOCl2. The solvent is usually dioxane, some polar aprotic solvent. But look at what's interesting about this. Here's our alcohol. Again, it's a 5-carbon chain. Actually, this is an 8-carbon chain, octanol. But we've got an alcohol on our 2-carbon, and this is R. It's in the R configuration. In the product, look what we have. The chloride is also dashed, the same way that the hydroxy group was dashed. This is a substitution, but we get retention of stereochemistry. Now, that means a couple things. It means that it is not SN2, because SN2 would give inversion of stereochemistry. It's also not SN1, because SN1 would give a mixture of R and S in our product. Also, remember that we don't have front side attack. There is no such thing as front side attack. So this is not SN1, it's not SN2, and it's not some imaginary magic dragon called front side attack. Here's the mechanism that involves conversion of an alcohol into a chloride with retention of stereochemistry using thionyl chloride as your reactant. It looks like this. Here's your alcohol. Here's thionyl chloride, your SOCl2. Just like we saw with the PBr3 reaction, the oxygen is going to add into our reagent. In this case, it's a sulfur instead of a phosphorus, and it's going to displace a leaving group. But in this case, the leaving group are pi electrons. Remember again that pi electrons are higher energy than sigma electrons. So that's going to be the better leaving group. That's going to get you this intermediate. The electrons are going to come back down off the O. Instead of kicking off the alcohol, it'll kick off one of the chlorines. That chloride can come back, grab the hydrogen, and get us back to a neutral molecule called the chlorosulfite ester. That's a stable molecule and can be isolated and purified. The chlorosulfite ester, under a little bit of heat with relatively warm conditions, will undergo this kind of cool rearrangement. This RO group will break. This RO bond will cleave, and the electrons will go onto the O, but that causes an ion pair. These guys don't separate very far. Rather, they kind of stick together and hang out, and almost immediately, those electrons will come down off the O, make a double bond to the sulfur, and that will cause the chloride to leave and hop on back onto the R group. That way we get our RCl and SO2. SO2 is a gas, and so it will bubble away, which means that we are constantly losing product, and that will drive any equilibrium forward by Le Chatelier's principle. So notice that if the alcohol attacks from the left and the thionyl chloride is on the right, that's a backside attack of that sulfur. The leaving group is the O. Eventually, once that O hops off, pushes the electrons down on the sulfur and pushes the chlorine back onto the R group, the chlorine is coming on from the side of the R group that the leaving group left from originally. From here, the leaving group left originally from the right side, the chloride came back on from the right side. So it's kind of like front side attack, but it's front side attack once the leaving group is left. It's like SN1, the leaving group leaves, but the nucleophile always comes back from the same face. There's never any time that the nucleophile is going to add from the back face to get us inversion. So we will always get retention by this method. So don't confuse the two, keep those straight. If you want inversion to get a halogen, use PBr3. If you want retention to give a halogen, use SOCl2. Remember, as far as reactivity goes, chlorines and bromines are pretty similar. They can both be eliminated, they can both be displaced. So whether you're going to do anything else to this product, if there's a chlorine on it or a bromine on it, really doesn't matter. One more thing I want you to think about. This is a rearrangement called a Pinacol rearrangement. Pinacol is a vicinal diol. The name of it is 2,3-dimethyl 2,3-butane-diol. It's a 4-carbon chain. It's a butane with 2 alcohols. It's a butane diol with 2 methyls on it. And if you react Pinacol in acid at 100 degrees, you will get a rearrangement. This is called pinacolone. And look at the rearrangement. First of all, our alcohols are gone. We had 2 alcohols on our starting material. We have no alcohols on our product. Also notice what's going on. One of the methyl groups has moved. This methyl group over here has moved onto the carbon on the right. And the alcohol on the carbon on the left, the carbon that lost the methyl group, ends up with a double bond O instead of a single bond OH. So think about this rearrangement. See if you can figure out a mechanism for it. I will go over the mechanism in class if you want. You can find the mechanism in the book. I'm sure it's in Wade. I think it's in Shermanis as well. You can Google it if you want to look up the Pinacol rearrangement. Just Google it. I'm sure there will be a Mastering Organic Chemistry website as your first hit. It's not an unknown mechanism by any means. It's a very popular mechanism. But you can use it as a synthetic transformation. If you want to make a ketone adjacent to a tertiary carbon, you can get there by doing a Pinacol rearrangement on a vicinal diol. It's a useful synthetic transformation. Try to figure out the mechanism. We'll go over it in class. Just for fun, here's a Swern oxidation mechanism. Remember I told you that the Swern oxidation is kind of the preferred method of converting secondary alcohols into ketones or converting primary alcohols into aldehydes in place of what PCC would normally do. It's kind of a fun reaction. It starts with DMSO, dimethyl sulfoxide, which is this guy. This is a resonance forms of dimethyl sulfoxide. That will react with our COCl2, and it will kind of do this decomposition process where the oxygen will add to the carbonyl, the electrons will fall back, displace a CO2 from here's C, double bond O, that's a CO2. It'll kick off a CO, there's CO right there, and it'll kick off a chloride, and you end up with the dimethyl chloride, dimethyl sulfide chloride. That will then react with our alcohol, where the alcohol oxygen will attack the sulfur. We will lose our chloride, and under basic conditions, we will grab one of these H's off of these methyl groups, and it will cause a decomposition where this kind of falls in on itself, and you end up displacing the dimethyl sulfide. You end up having a C double bond O. That's our carbonyl group. So 2 things that are going on here. We're displacing gases. We're losing CO2. We're losing carbon monoxide. We're losing dimethyl sulfide. We're losing lots of gases, and anytime you lose gas, that drives the product forward, drives the equilibrium forward to make more product. Secondly, one of those gases is dimethyl sulfide, which is the smell of rotten eggs. So when you do a Swern oxidation, you let it run for a few hours, you come back and the entire lab smells like rotten eggs, you know your reaction is done. You also don't want to go in the lab because it smells terrible. Yes, we are displacing carbon dioxide and carbon monoxide, So again, you want to be careful under large scales that you're not generating lots of toxic gases. You always want to make sure that you have good ventilation in your lab. But nevertheless, it's better than chromate, that's for sure. And it's a lot more gentle. So that's it for alcohol reactions. That's the end of lecture 2. Our Stromanis chapter is chapter 10 or 16. Those are both involving alcohols and synthesis. You can work on problem set 1. Remember, that's due Monday. I also encourage you to work on alcohol reaction maps. Those are the 3 things you can do before we wrap up alcohols and reactions for a while before the midterm.